Good afternoon, ladies and gentlemen. We're very excited to host Dr. Saptarshi Bandyopadhyay from JPL. He's a colleague and a friend of mine. So let me read his bio. Dr. Saptarshi is a robotics technologist at JPL's at NASA's Jet Propulsion Lab in California, where he develops novel algorithms for future multi-agent and swarm missions. In 2020, he was named a NASA NIAC Fellow for his work on the Lunar Crater Radio Telescope on the far side of the moon. He received his PhD in aerospace engineering in 2016 from your favorite university, University of Illinois, Urbana-Champaign. He earned his bachelor's and master's degree in aerospace engineering in 2010 from Indian Institute of Technology. So we're very excited to have you today and looking forward to hearing what you have to say to us. Thank you.
Thanks. Hi, everyone. Am I audible everywhere? Good. So before I begin, I want to say that it's a great honor. Like 5 years ago, I got my PhD from this university, and I'm back giving a talk on a project. I do want to say something about the AE 590 course that many of you are here for. I really enjoyed these talks. I didn't understand their use when I was a student here, but now when sitting 5 years later at JPL, I remember, oh, I heard this in a combustion talk. I'm from the guidance navigation and control field. I heard this in a combustion talk, and that really makes sense why there is a communication blackout when my spacecraft is entering through Earth's atmosphere. There are going to be connections that you'll hear in these talks that are not going to make sense, or you might think they're useless, but they really matter, and I hope you'll enjoy them. Not just this one, but all of the series. So trust me, it's a good thing. So with that, I'll begin. So this is a project. We're trying to put a kilometer scale telescope on the far side of the moon. In this talk, I'll talk first a little bit about the science. Why do we want to do something like this? Because it's going to take a lot of money and a lot of taxpayer dollars. So you're all invested in this. And then I'll talk about the technology behind it. How do we make that happen? A project of this scale cannot happen without a lot of people, not just me. So I just happen to lead this project. Let me try to see if I can reduce the bar over here. Doesn't look like, I don't see how to do that. Do you know how to do that? Bring the bar down. This entire thing so that the people can see the names. Okay, more and hide. Okay, great. So that's just some of the team members. There are a lot more people, and I'll show you a team slide later on. So with that, let's try to jump right in. What are we trying to do? Yeah, so before that, why did I start thinking about a project on the far side of the moon? My name, Saptarshi, means the Big Dipper constellation. So I've been forever interested in astronomy for quite a part for all my lifetime. And I was actually doing some research at this giant meter wave radio telescope, GMRT, in India, for part of my undergraduates trying to study the Rho-Fuki cluster. And one of the things that happens when you do study radio astronomy is you realize very quickly that we don't know what the universe looks like at wavelengths longer than 10 meters. Why? It's because of this reason. The Earth's atmosphere allows certain wavelengths to come through to Earth and does not allow certain wavelengths. So we call that atmospheric absorption or atmospheric opacity. So you can see on the curve over there, the wavelengths longer than 10 meters are not visible from Earth. The ionosphere actually absorbs these wavelengths and then turns them around and also reflects it. So ionosphere is a strong source in these wavelengths. So if I were to put a telescope on Earth, the ionosphere won't let those waves come in. If I were to put a telescope around in Earth orbit, the ionosphere will still be such a strong noise source that all the signal will be garbled. You can see where this is going. You all know that the moon is gravitationally locked towards Earth. So only one side of the moon faces Earth. So the far side of the moon never faces Earth. So I told you Earth is a strong source. So where would you put a telescope? You would put it on the far side of the moon. So that's why we are trying to put a telescope there. Turns out there's also a couple of additional things that happen. The far side of the moon is a pretty good, like the moon basically is our shield from Earth. It also shields us from the sun during the lunar day, where the sun is a strong source. So now we have all these waves coming from the far side or coming from the early universe that are nicely shielded from the Earth and sun. So that's why we are putting a telescope there. But clearly, these ideas of large telescopes of this size has been around. This is the recently dead Arecibo telescope on the top over there. And now the biggest telescope on Earth is FAST, 500-meter telescope made by China. But if LCRT is built, it would be a 1-kilometer telescope, would be the largest field aperture telescope in the solar system. I like to call it that way. So, it's not on Earth. So the idea of a telescope on the far side of the moon has been around for a long time. It's been around from the 1960s. This is when humans started thinking of sending other humans to moon. And we're like, why should we do that? Oh, we should study the universe that we can't observe. And these are some pictures. The picture on the left is a 1984 picture by Professor Jack Burns, a professor at Colorado Boulder. And so this is before I was born. So that kind of shows this idea has been around, but everyone thought this is really, really hard. In fact, these are the 4 technology areas that all the literature till now, before we got into the picture, they pointed out these are the technologies that you need to make this happen. So I was a young researcher, came out fresh out of UIUC, started my work at JPL. And I was like, hey, I do space robotics. Maybe I could hit these technologies and make this happen. So the 4 technology problems are selection of a lunar crater, Arecibo type support structures. I'll try to show you here. There are these tall support structures. And now these are hard because Arecibo, this is the support structure that kind of broke. And although Arecibo was surviving for 50 years in Puerto Rico, which is a high intensity hurricane environment. So it's a pretty good design, but still those are hard to build. Thermal strain compensation. Moon goes through these temperature cycles of almost 250 degrees centigrade from a lunar day to lunar night. So thermal strain compensation is hard in the best of times. And then rim to flow transportation. If we're trying to build something inside a crater, it has to go up and down the crater wall. So hopefully in today's talk, I'll be able to convince you we have good solutions to all these 4 things. And again, I must say that I am a aerospace guidance navigation control engineer at heart. So I'll try and talk about the science and the physics and all the things that are necessary to make this happen. But there's a large team behind it who are enabling all this. So what is it that we're trying to build? So I like to use this picture that kind of puts it in perspective. So we'll find a 3 to 5 kilometer crater and then put a 1 kilometer deployable reflector inside the crater and then suspend it all with wires. You can see solar panels and communication system outside the crater. And this is another side view of it, I think. The entire thing is suspended inside the crater. So immediately, the first thing, we don't need any of those strong foundational elements that lift the receiver above the brush, which is common in all the Earth-based pictures. You see, everything is inside the crater, and Moon has 1/6 the gravity of Earth. So suspending something on the lunar surface is significantly easier than building structures and building things up. You would see a lot of engineering tricks played across this mission, basically because it's being designed by engineers to enable how to solve these problems that we talked about. Actually, this was the cover art of issue came out by the Philosophical Transactional Royal Society, but they were talking of astronomy from the moon the next decade. So let's go deeper into the science. What is it that we are trying to observe? So you have this nice picture over there. On the left-hand side, you have Big Bang and then the cosmic microwave background radiation. And clearly there's a lot of work happening on that front. There's a bunch of spacecrafts that have been taking data. On the right-hand side is present day, right on the edge of the right-hand side. And you have also Hubble and now soon to be launched JWST that will look at the universe in relatively newer stages. But there's a large region in the middle, like the cosmic dark ages, the first stars, that is almost impossible to see with any existing or planned mission. So that's what LCRT is trying to do. So there are also a bunch of Earth-based observatories shown above over there, but I talked about the 10-meter limit. So none of them can also see in this data. And that region is where what we are trying to observe. So this is a picture of the Hubble ultra deep field, just for those who aren't aware, each speck over there is a galaxy, not the ones in the front, the very far away stars, or those points, so they're actually galaxies too. Here's a picture of the cosmic microwave background, so that's on the other end. So you saw that these are the two data points we have, the Hubble ultra deep field. Potentially we'll have a JWST ultra deep field in the end of this decade. And we have the cosmic microwave, and nothing in the middle is known, and we are trying to fill that, a part of it. I also like to show this picture to say that every part of the universe that we have observed has given rise to Nobel Prizes. So there's a lot of Nobel Prizes given out for CMB research, a lot of about the structure of the universe. Goober Prizes and astrophysics have been given up, but there is no Nobel Prize in that region, which we're trying to observe. So what is it that we are trying to observe in this picture? So what is this thing at the bottom? The thing at the bottom is neutral hydrogen. So the universe at this region, just after the hot Big Bang, was pretty simple. It was mostly made out of neutral hydrogen, dark matter, dark energy, and a lot of antimatter that we don't know. So what is this neutral hydrogen that I keep talking about? So from basic chemistry, you guys would already know, quantum mechanics and chemistry, that hydrogen, when its spin of its electrons flips, it gives out a radiation that is 21 centimeter in wavelength or 1420 megahertz in frequency. I live on the world of wavelengths because it's much more easy for me as a physicist, as an engineer to understand. So a 21 centimeter wavelength is about this much. Now you're also aware of this concept called Doppler redshift. You know, when a train moves closer towards you or away from you, the velocity, the frequency changes. The same thing happens in space. So when a star is going farther away from you, its wavelength of the light reflected or emitted by that star increases in frequency, or reduces in frequency and increases in wavelength. So the light becomes redder. Now we know that Edwin Hubble, on whom the Hubble telescope is named, he found that even galaxies are drifting away from us. Not just that, the galaxies that are farther away are drifting away at a faster rate. Well, there's a separate problem at what speed they're going out, but leave that aside. We know that almost all galaxies, as they move farther away from us, are moving away at a faster rate. So which is also similar to, they're also farther back in time. So if we multiply this cosmological redshift with that 21 centimeter wavelength, what we get are wavelengths that are of the order of 10 meters to 100 meters. So the cosmological redshift, I don't know if it's shown here. Yeah, it's of the order of 1,000 gives rise to wavelengths that are of the order of 100 meters. So just to say another way, a 21 centimeter wavelength emitted from a hydrogen atom is emitted so far back in future that that wavelength, due to Doppler redshift, has now increased to 100 meters. It's phenomenal, right? I mean, every time I understand that, I get crazy. Anyway, so we are not the only ones who are trying to do this. LCRT is shown over there, but there's a lot of other mission concepts out there. In fact, I wouldn't say we are even the first kids in the block. There are a lot of really good missions out there. Farside, led by University of Colorado Boulder, is in my opinion the top foremost priority in this field. But we are trying to catch up, and that's some of the science that we want to do. So let's go a bit deeper. Okay, so why do we want to do this? There are also some questions like, is our universe accelerating, decelerating? All of these questions that we have good theoretical ideas, but we don't really have mathematical knowledge, or we don't have experimental data. And we might be able to collect all of this data, because one of the cool things about observing the neutral hydrogen line is that it gives you kind of a time lapse of the universe in that region. So we can actually measure both the growth and the rate of growth of the universe in those wavelengths. Another big question that we want to understand is, what is dark matter? What is dark energy? Most of you are aware of that the normal matter in the universe is like barely 4%. There's a huge uncertainty, it's like almost 95% of dark matter and dark energy that we kind of don't know what it is. Our contention is that looking at the universe, the simple version of the universe, where there was only hydrogen, dark matter, dark energy, might be a good way to put bounds on what we understand these. Like, these are just ideas. Now I'll give you the most crazy science fiction idea, because again, I am an engineer. We don't really know we have so much matter. Why do we have so little antimatter in this universe? Why is that exciting? Because if we figured out how to create and how to what causes antimatter to just go away versus how can we make them stay or make them stable. We could potentially design antimatter engines where matter plus antimatter equal to energy, and we could potentially have extremely efficient, extremely fast engines. These are science fiction ideas, but they're actually being funded right now. So this is a good place also for you to think crazy ideas and then try to take them to the extent of the technology we have and maybe start building them. So anyway, that's what drives me, that maybe 100 years from now, we'll have antimatter engines. Another thing I use to motivate people to worry about these problems is think of our understanding of physics 100 years ago in 1920s. We are barely understanding what is quantum, what does the atom look like. And today we have this exciting universe of computers, internet, satellites, all built on that science. So a few more leaps in technology, especially physics, would change our understanding of the world and the way our grandkids live forever. So let's enable that. So that's what we're trying to do. Not the entire thing. We're just trying to look at a part of the universe, but that's the giant goal, that's what exploration gives us. So let's now go a bit deeper and really understand what is it that we'll measure. So we'll measure this signal that we expect to find. So you can see on the right-hand side is our best estimate of what the signal would look like. These are all different temperature, so difference in the temperature of the background versus the signal. And the region in yellow shows which regions LCRT will observe. And this is a paper taken from Purna Leto and UCLA. And what you'll see is there is almost an order of magnitude difference between our best cosmological models today. So we kind of don't even know what we're going to observe, which is fair, right? We don't know what the universe looks like. So we are basically trying to design our sensitivity, and everything comes from this graph, where we have to ensure that we can differentiate between those lines and potentially build a new line if the signal says so. So as I said previously, this is different from CMBR, cosmic microwave, because cosmic microwave is one time shot, whereas we can potentially get a time lapse. So that has a lot more data in my eyes. Then finally, this allows us to constrain things like intergalactic medium, the state of large-scale structures, dark matter, and inflation. Inflation is a crazy thing. We often assume that the largest thing in the highest speed at which something can move in the universe is limited by the speed of light. General relativity says so, and special relativity says so. But turns out space itself can move at 1,000 times the speed of light, or significantly faster. Supposedly, our best understanding of inflation is that the space expanded at huge multiples of the speed of light. I do not understand this. There's a physicist here, maybe you can explain, but that's our best understanding of the world today. It's crazy. And we are going to be looking at regions where inflation might have played a role. Then the strongest signal that is going to start troubling us is our own Milky Way galaxy's radiation. The curve over there shows that a Milky Way galaxy signal in these wavelengths is 5 orders of magnitude stronger than the signal that we are observing. But we know a lot about the Milky Way galaxy signal, so potentially we can remove it. But we are actively working right now on designing the instrument to make that happen. But we are also selecting our position on the lunar surface such that we are out of the really strong region. So on the bottom, you see a curve where the Milky Way noise source is shown. And each of those lines show, if I were to put a telescope at a certain lunar latitude, where would it trace on the lunar surface, or on the galactic surface? And you can see if you put something around between 0 degree to 20 degree north, we would see a pretty large section of the sky, but we would also miss that really strong peak between around 20, 25 degrees south. So that's what we are trying to get. So with this, I have covered the science. So now let's start diving deeper into the technology. This one is kind of a key overview of what the LCRT would look like. It's a 1 kilometer size reflector. We're trying to put it somewhere in the 20 degree north. That's what it told me. There's also another location requirement. It's like 180 degrees plus minus 45, because the figure on the right shows that if you you could see at different wavelengths, you still have the radio interference from Earth that could seep in. So only the blue region right at the bottom is right on the extreme right. That is the really radio quiet region. So we want to sit right there. Other things over here, another operational life of 1 year, that comes from that curve at the bottom, which means if we integrate the data over 1 year, we'll be able to replicate for that strip on the galactic screen, we'll be able to replicate what the universe looks like. Only for that strip. So it was not going to be an all sky map like you have been used to seeing. This is going to be a small strip, but that's where we start. Now the second, so we talked about the anchors and how we are getting rid of the foundational elements by not essentially having any foundation elements. The second thing is craters, finding craters on the lunar surface. LROC, or Lunar Reconnaissance Orbiter, is a spacecraft that went up, I think, around 1990s, 2000. I'm not sure of the exact date. But basically, we were looking at 3 to 5 kilometer craters, and you can see there are like 82,000 craters. So finding craters was not a problem. Now, weeding them down and selecting our favorite crater became the problem. That's not hard. We could go and look at, very nice tomography maps, and everything is available on the LROC webpage. Here is our selected craters on the right. We looked at 50 craters in extreme depth, and finally we selected this crater. These are all in published papers, so I'm just going through them quite quickly. So you can see it's a 3.8 kilometer crater, and it's 960 meter in depth. And the distance from the mesh to the receiver at the top is like 600 meters. So all of it can nicely sit in the 960 meters. So which is great, so that takes care of a second problem. Now the third problem, okay? So how do you design a mesh? And the biggest problem with this mesh is that it has to survive 300-degree temperature fluctuations. So the way you go about it, so before that, just some nomenclature on the left. These wires that are going from the central hub all the way to the extreme end are called radial wires, and the wires that are going around the telescope are called circumferential wires. So the picture on the right shows something all of you are aware of. If you take two wires, if you take a wire and hold it in two ends, you get a catenary shape. We proved that in calculus. We proved that many, many ways, right? It's a fun problem that all of you have done. Turns out if you just change the mass density, you can give it any shape you like. So here is a mass density given 1 by cos squared theta, and that gives it a circular shape. You can see where the engineers have come in. We take that problem, take it into a parabolic shape. So don't read much into the equations, but the point is that's the trick, that if you can change just the thickness of the wire at different places on the mesh, you get a shape that does not depend on temperature, because when you heat or cool a mesh, it uniformly expands and contracts. So now 300 degrees centigrade, you throw at the problem, it doesn't change anything. The mass variation remains the same, the shape is maintained. Again, an engineering trick to get rid of a very, very painful problem. So this is the mesh, a good realistic view of the mesh. Let's go a zoomed in view. A problem with this mesh is that it's 1 kilometer in diameter, but maybe let me go back one more and let me show you over here. If you look at those math equations, and if you look at the circumferential wire thickness, under that math, to get that parabolic shape, the circumferential wire thickness has to change from 1 millimeter to 1.8 millimeter. So these are very precisely manufactured mesh. So we have to do our analysis at that scale. So we have to be true to the scale of this problem. This scale of this problem spans 1 kilometer in diameter, but our mesh thickness is of the order of millimeter, and we have to be true to it to get all the FE analysis. So currently our computers are breaking. We have to figure out how to fix that problem. So we are working on it. Okay, so now the wire mesh, a kilometer scale wire mesh, has to survive 4 interdisciplinary constraints. This is what we are actively working on right now, actually. It says future work, but we're actually doing it. We got recently funded by a NIAC phase 2, for those of you who know what it is. Yeah, so we are actively working on this. So it has to survive structural and thermal analysis. From those of you from FTA would really understand this. You have lunar gravity 1/6 of Earth gravity. You have the 300-degree temperature fluctuation. It has to deploy from a stored configuration. So it is most probably going to be taken to Moon on a rocket, and the rocket is limited to 10-meter diameter. So it has to open up from 10-meter diameter to 1 kilometer in diameter. So it has to be deployed like an origami. I'll show you some ideas. It has to have perfect RF performance to get the science we want to get. And finally, it has to be launchable, so that we can't make it out of, iron or something. So these are 4 interdisciplinary constraints that will define our mesh. So we have this nice multi tool setup, because to design a mesh of this query, you need a lot of Python, MATLAB and Python stuff. But then it gets fed into Abacus, where we do the FEM. Here is our model. It's a 100-meter model. Here are some simulation results. So the obvious question you would ask is, what are the boundary conditions for this FEM analysis? Right now, what you'll see is a boundary condition where the entire structure has been held in place. Like the outside is completely, static or stationary. But that's not true, right? You can't build a structure like that in space. So the next thing, okay, before that, another trick that we are using. What is the temperature fluctuations that we need to worry about? I told you about the 250 degrees temperature fluctuation. But because we are interested in science that happens only during lunar night, our main design has to survive. It has to be robust to the 250 degrees centigrade. That means the structure should not break. But the shape should be maintained for only those temperatures when we are actually doing science. So it turns out, if you look at the data closely, this is on the right is the data of the temperature on the lunar surface and the deviation from the mean. The top picture is the mean and the bottom picture is the deviation. There is only 10-degree temperature variation during the lunar night, which is expected. Moon does not have any convection. Moon does not, only thing is radiation. So we have to maintain shape for only 10 degrees Kelvin, but we have to survive 250 degree Kelvin. That's much easier to do than trying to maintain shape over 250 Kelvin, in spite of the tricks that we are pulling. So that's what we are using. And then the next question is, how many lift wires do we need? So it turns out we did the math, and given what wires exist, we need 16 lift wires to lift up this 2-ton mesh, and 4 lift wires to lift up the 50 kg receiver system. That's trivial math, I think all of you will understand. So with that, here is a better design that shows for a 100-meter scale or a 50-meter diameter antenna what we can do. I told you our FE analysis was breaking for the 1-kilometer scale. So we are actively working on supercomputers right now trying to make that happen. But these are 50-meter scale results. Things seem to work. Then the RF performance of a mesh like this, turns out you might be wondering, what is this mesh that I keep talking of? If I take an aluminum foil and spread it out to a kilometer in size, it's going to weigh a lot more than 2 tons. So what is this weight? Think of this mesh like a fishing net. A fishing net has big holes. Now, the question to ask is, what can be the size of those holes? Because the bigger the holes, the less mass I need to carry. There's this rule of thumb that if you want to do any measurement in any wavelength, if your holes are smaller than lambda by 4, so lambda is the wavelength, lambda by 4, more or less the wavelength is not, the signal is, the RF or the electromagnetic spectrum will not see those holes. So that holds true in optical, in any wavelength, any electromagnetic spectrum. So that gives you an upper limit of my holes in the fishing net could be 2.5 meter cross 2.5 meter. So just think of how thin this mesh is. We were thinking of 1 millimeter wires with massive 2.5 meter cross 2.5 meter holes. And I guess now you're seeing why it is just 2 ton in mass, right? It's actually a very, very, very sparse mesh. So, but when you give that design to an RF engineer, they don't like it because that was a rule of thumb. Here are the numbers on the table that shows for different gaps or the mesh inter-mesh distance, how much I will lose in sensitivity in dBm or gain in this case. So gain is my sensitivity of my mesh. So you'll see on the large wavelengths, so like 3 megahertz is equal to 100 meter wavelength, there's almost no loss in gain. But on the small wavelengths of 30 megahertz, which is 10 meters, it's like an 8 dB loss. Now the question that is important to ask, of course that's an 8 dB loss, but can my science instrument still get me the science in spite of that loss? Or do I need to increase the density of my mesh? We are actively working on that. We don't have an answer. We're doing a forward model where we build the entire science in a simulation software and show that yes, we'll make this work, or it won't work, and we have to increase the density of the mesh. Another thing that we'll have to worry about is the feed. Like all this time I was talking about the mesh, which was a kilometer scale mesh, but there's going to be an antenna on top of it. Like all big antennas need a feed on top where the actual signal is collected. If you use a simple log periodic antenna, it's going to come out to 150 meters. Our current design has reduced it to 100 meters. But there's a problem here. Like there are many nice log periodic antenna designs. I saw one in your lab today that we could use. But the problem here is we don't know what the signal looks like. So we have to have a design that is so clean in RF terms, that is so clean that we can analytically work out what it should be doing, and then go through and check what our results look like. Because there's no calibration source. There's nothing I can do to predict this is what the signal should have been, and hence this is my calibration through the mesh. So yeah, we might be using a 100-meter scale log periodic antenna of that design. But if we can design deploying a large log periodic antenna of that scale has been done in space, not 100-meter, but 30 meters has been done in space. So we could make that happen. Okay, so now finally, how do you launch this and how does it reach the moon? So this is a concept of operations. The idea that we initially had was to take a spacecraft, break the spacecraft into two parts. One part would land on the crater floor, one part would land on the crater rim. And then on the crater rim, you would have these cool rovers. I'll show you a video of the rovers next. These rovers would go down, pull on the wires, and bring those lift wires up. We would anchor those lift wires on the crater rim, and then the mesh would deploy on those lift wires. So that's the idea we are working on right now. What are these rovers? You remember one of the 4 challenges was rim to floor transportation. So with this, we are basically rounding off all the issues that were pointed out. This is the rover we'll use. This is just being in the right place at the right time. Let me show you a video while I'll drink some water. By the way, if anyone has questions, please feel free to ask now too. I'm happy to take questions, and obviously there'll be questions at the end. So you can see the rover broke into 2 parts. One part anchored on the top, on the crater rim. The second part is going down. The tether is very important. The 2 robots are connected by a tether. Because going down a steep slope, you can't just come up very easily. You need to be pulled in, reeled in by the tether. And this is actually being done autonomously. So this one autonomously navigates and goes down the crater floor, and you will see it also coming up. This was built in JPL over the last 20 years, and we are trying to go down Lunar pit. And I was lucky this rover was there, that we could use it for our project. And there it is coming up now. So you could envision that robot would have a small arm or something on which we'll grab a wire and bring it down, bring it up from the crater rim. And there it docks. Hopefully the wire gets anchored to the crater rim, and then this rover walks away to the next location. So I hope I've convinced you that yes, rim to floor transportation is not a problem anymore. So this is our ConOps of how many rovers should we deploy. So the 3 examples on the right are all using rovers. You can see the rover line over there, the second line from the top, 1, 8, and 20. So we need 20 total anchors. So you could potentially launch 20 rovers, but that would cost, right at the bottom is our cost. So these are all rough order of estimate costs. They're like $4.5 billion. That's too big, I would say. But you see the case with 1 robot is like 1 billion, and maybe we could extend that to 2 robots. So we have like, some risk aware, risk assurance and all. That takes it to 1.2 maybe billion. That's very good, because today on Thursday, the decadal survey on which NASA decides how to spend money, the decadal survey came out, and supposedly there is a Dark Ages probe that would have a budget of 1.5 billion. That was on the decadal survey. So not this decade, but next decade. So we are very much on the run for that project. On the leftmost column, there's a different idea that we were trying to explore. What if you could just shoot harpoons from the crater, from the lander in the bottom? Then you didn't need any of these robots and anything. We're doing some math. Turns out it's not working, but that was a cool idea. We are looking deeper into it. So here is work. Again, I told you I do multi-agent systems. Here is some work on how many robots do you need to build. So one of the key things, so there's a comparison between a 5-robot case and a 2-robot case. And what you'll see in the top picture is everything gets built before lunar night sets in, which means the robots themselves don't have to survive lunar night. They can just die during lunar night. The second one, option at the bottom, uses only 2 robots, but these robots have to survive lunar night. So we're trying to understand the pros and cons of making the robot survive lunar night versus reducing the cost of having multiple robots. So finally, we'll think of how do you package this? How do you deploy these lift wires, anchor them, and deploy lift antennas? So let's go deeper. The packaging lift wires, turns out there's a lot of work being happening in origami field. What you see here is a picture of a star shade. That is a 10-meter folded origami structure. And we are going to use something very similar. I'll show you the fold pattern a little later. But that fold pattern could be essentially extended all the way to kilometer scale. So packaging a kilometer scale antenna into a 10-meter launch vehicle is something that is feasible. We need to prove it, demonstrate it, increase TRL, but it's feasible. There are many deployable lift wires, deploying the lift wire options out there. We are choosing the robot option, which is again shown on the right. Everything that we have selected is shown in red. If any of you are interested in knowing more about this, or you want to do some research on similar ideas, this stuff is out there on our website. So if you just search for LCRT, you'll find all of this. We publish papers. There are other options on how you would deploy lift wires using rovers. I'm not going to go deeper into them, but we could potentially throw out mass anchors, which the rover goes and anchors to, things like that. But we are going to go with the simple tethered rover option. Finally, one of the interesting things that happens on the moon is that we're talking of these large cables, right? These are kilometer scale cables that have to be carried from one region to another. The lunar surface, actually, the lunar regolith is very sharp. It has never been eroded like it has been doing on Earth. The lunar surface has become the way it has become mostly because of thermal cycling and micrometeorite hits. So it's extremely sharp. So if you take a piece of really reinforced cable and drag it on the lunar surface, you might break the cable very easily because the lunar surface, the lunar regolith will just go in and just keep cutting onto it. That's one of the reasons why the astronauts were very afraid, because if the lunar dust went into their body, it will just keep eating into their body. So that's been a problem that we still have to figure out how to solve before we send astronauts permanently on the moon. So our design is such that there's only going to be one point of contact at which the cable will touch the lunar surface, and that contact point won't move. So that's why we are using a two-way tether system where the duaxle has a tether so that the duaxle itself reels itself up on the crater floor, on the crater walls, and at the same time the duaxle maintains a tension of that wire that it is carrying from the spacecraft so that that wire never drags on the lunar surface. Anchoring on the moon is exciting and difficult. You could think of anchors that are great for lunar regoliths, like sandy, beach sand. That's what people think. Because you see, we only went to the near side of the moon. So we actually do not know what the far side of the moon, what it feels like, what it looks like. So near side of the moon supposedly felt like beach sand. I don't know what you want to make of it, but there are a number of lunar regoliths, simulants out there. But since this is a big mission, you also have to be aware or capable of handling the case where we go up to a place and we see only barren rock over there, right? Like you can't launch a multi-billion dollar mission and say, oh, by the way, we designed for beach sand and it looks like it's all rock here. So we have to figure this out, either with a lot more data or with an anchoring system that works across multiple, from beach sand to barren rock. We do not have a solution. We're still working on this. The other part is, how do you deploy a mesh of this scale? This work is on the rightmost option is our selected option is we want to put a pulley over there. And you might wonder why there are already 2 wires. But putting a pulley over there does some interesting things. It allows you to control the deployment completely using the single lander sitting at the bottom. Now remember, we're deploying something a kilometer in scale. So you want very good coordination. Having a centralized coordination which can deploy slowly is, in our eyes, the best way to do it. So that's how we are going about doing it. For all other options require us to do the coordination somewhere else, and we don't like that. The centralized lander will have a lot of computing power. This thing has been done on Earth. Like, there are these nice demonstration videos where you could move things around and move people around. You know, this is also a very good way to simulate motion in space, like astronaut training and all can happen like that. It's also for fun. You can go and check it out. So this is how we plan to deploy the liftway. I told you that I'll show you an origami deployment mechanism. So that is our fold pattern. So that fold pattern multiplied n times, I'll show you in the next slide, gives you a fold pattern that allows you to deploy something from 10-meter diameter on the launch vehicle to 1 kilometer diameter once deployed. So again, this is again our abacus model. For those of you who are interested in FEM, we're using a different model for this. Again, the same pipeline showed previously. On the left-hand side, you can see the fold pattern that we just talked of. There's an interesting thing we discovered when we started using this fold pattern. This fold pattern supposedly is bistable. That means that you first keep applying force and the fold pattern opens up, but it only opens up to 90% or actually 92% or something. And then for the last 8%, the pattern on its own opens up because it crosses a bistability, and then the open configuration is the preferred configuration. That's great because that means once deployed, the system will not try to collapse on itself. But it's also not good because suddenly you have opened it to 900 meters, and the last 100 meters, the thing will try to deploy on its own. That would produce a lot of interesting stresses and strains on the system that we have to worry about. Because all this while the system is under a tension load, and suddenly the system moves into compression load. Stuff, again, many of you would relate to, and we need to worry about that. We're trying to do parametric analysis for the different properties like Young's modulus, wire thickness, number of folds, intermediate folds, and all to understand what this looks like. Here is a very different geometry. Here, if you were to just stack it in one fold, not have those intermediate folds in the previous design, how big would it have to be? It is around 80 meters in scale. Turns out this is not what we'll do, but the force and the torque values that we get from here, and this is a kilometer scale deployment. So the force and the torque values that we get from here are a good first order estimate for designing our remaining, how many robots we need, how much force it needs to give, and things like that. A project at this scale, we are too young. As you might see, most of our big questions are unanswered. We are still not even a real project, not even a NASA project. We're too young, but a project at this scale usually does not have a risk list. But we are maintaining one because this is a there are a lot of superlatives, largest, biggest, a lot. So we need to really understand what our risk posture is and bring them down over the multiple years. This is another way of looking at the same picture. So finally, all of this is heading towards trying to build something like this on the far side of the moon. In this talk, I showed you a bunch of things. The LCRT concept is trying to measure the world, the universe, in the 10-meter to 100-meter wavelength band. If successful, this would be opening a new window into the universe. There will be many technical challenges that need to be addressed. I just spoke about a few of them. We didn't speak about many things like that are not, in my eyes, big technical challenges, but we didn't speak about communication, for example, and others. And I think this will create a lot of public excitement. Having something of this scale sitting somewhere on moon will enthuse people. So yeah, there was a lot of coverage on it. It's still going on. There's somehow a comparison to the Death Star. I don't get it because the Death Star, this thing is pointing away from Earth. I mean, get the geometry. Anyway, so this is our team. There's a lot more people working on it, and we are actively working on it right now. So with all this, we're trying to make LCRT a reality. Thank you, and I'm happy to take questions.
Thanks for an excellent talk, Saptarshi. Questions for Saptarshi? Probably need the microphone.
Thanks so much for the presentation. How crucial is it that the lander in the crater floor is perfectly centered in the crater floor?
Actually, that triggers another interesting question. So firstly, it's quite crucial because we don't actually have a locomotion mechanism that we're not thinking of, because our lander is already going to have a 2-ton mesh, a receiver system that is quite complicated. So we don't want to do that. Turns out there are 2 interesting tricks that we're going to play. One is, you might have seen the recent landing on Mars, where we use terrain relative navigation. That is, we understand the terrain that we are going to go to, and then we kind of do pinpoint landing in that terrain. On Mars, the problem is harder because Mars is so far away, so everything has to be done autonomously. On Moon, technically, there are a couple of other other companies, I don't want to name them, but they are basically building hardware that potentially could hover on the Moon. So once you can hover, you can increase your accuracy massively. So we would like to be within, say, plus minus 100 meters of where we want to go. And that sounds within the capabilities of what these companies are claiming, because you need that for human landing on Moon. That's part 1. Part 2 is, I talked about our initial idea was to break the spacecraft and send it in 2 parts. One of these human landing capabilities, again, don't want to take the name of the company, but is that they could potentially hop on the lunar surface. So that makes life much nicer, because now you have only one spacecraft, and you could take the spacecraft, first land all the heavy equipment on the crater floor, hop up, put the robots on the crater rim, and then fly back to Earth. So yeah, it's a good question.
Hi, thanks for the presentation. You might have just kind of answered this, but do you see, as we increase our work towards an increased presence, human presence on the Moon, do you see any role of crew interaction in the deployment of this?
Yeah, so this is a kilometer scale thing sitting on the far side of the Moon. Most probably, if we send humans, we want to put them on the near side of the Moon, so that they can communicate with Earth. First thing. Secondly, I personally come from the robotics background, and one of the things you might have noticed is, if you have ever worked in a drone lab, is drones tend to hurt humans. Now, humans on Earth don't wear spacesuits. So just think about these robots will have sharp edges. How close can they come to a human? They have these long wires coming out. If the wire breaks, there'll be a nice whiplash that will take out anything in the nearby vicinity. So robots and humans in space don't really gel well. That's not to say that there's not a place for robots and humans together. But if I want to build something of this scale, especially if there is a way to do it without humans, I would go that route. There are examples and experiments and all where you need humans. They have to work together. But I personally am trying to push it away from humans because of those reasons. Yeah.
Other questions?
Hi. So my question is, what are the benefits and limitations of having a telescope inside the crater?
That's a very neat question, because technically we could have kept it on the lunar surface, right? So one of the things that happens when you put it inside the crater is you get to suspend everything inside the crater. So you get rid of all the large foundational elements that Arecibo had, those really huge support structures. Actually, just to give you a feel for what we are talking about, let me show you what these support structures of Arecibo looked like. Because I had a picture of Arecibo right here, right? So this one, you see this? This is like a huge 20-story support structure. So that is already Arecibo being inside a crater. So Arecibo is a crater. That's what the telescope is named after. You still have these 20-story support structures on top of it. Building like that on the moon is almost impossible. Like, it's too hard. So that's why we want to be inside a crater. The second thing that trick it does give us is if you are communicating, you will create radio frequency interference, the noise that we are trying to avoid. But if your communication equipment is outside the crater, then the crater protects the telescope from the communication equipment. So that's the second thing that happens. But the crater has disadvantages. So you won't believe this, but on the moon, the lunar dust gets levitated, and a kind of a haze forms during the lunar day, early dawn and near dusk. We do not have any scientific pictures of this. We do not know this, but astronauts had seen this, so we want to believe it. So we have no way to confirm that it. Actually, I'm working on a project proposal, literally trying to find scientific evidence for this, because the lunar dust is electrostatically charged. That's the only mechanism we can think of that is levitating the dust. This is an RF equipment, so it's most probably going to get electrostatically charged. Chances are that dust will nicely get attracted to this mesh. Now you have a kilometer scale mesh picking up dust because it's just getting attracted. So the mesh weight will just keep increasing. So these are really crazy things that happen on the moon that we need to worry about. And that our current models of the dust is that lunar crater acts like an amplifier. More dust gets settled in there. Yeah, it's crazy. The moon is a fun place to work with.
So obviously you have a whole lot of unknowns in this mission. On one of your slides, you had the mission lifetime as 1 year. I was wondering, is like the thermal cycling the limiting factor for that, or is it something else?
No, so the slide with 1 year was, given the amount of time we are going to observe, how much time will it take to collect the science data that we'll collect? So that is what 1 year said. If we are going to launch something like this, I don't think NASA will give us money if we're going to die after 1 year, right? So most probably we'll have to live for many, many more years. At least I would say 10. There's also an interesting caveat to that story, is that success of a mission depends on when you collect the main science and also what else can you do on top of it. So for example, you might have seen the Mars helicopter that is on Mars right now. It's had its 15th flight, I think, already, or something like that. But it was only designed to succeed for 5 flights. Everything we're getting on top of that is bonus. Actually, that was designed in my section and JPL. So success of a mission is defined by how long do you need to survive to get the job done. But you don't usually design just to get the job. You design for enough leeway, because if something exciting comes up, we want to go back and redo that math and redo those measurements again. Although nothing here is moving, so we are going to get the same data again and again, but there is an 18-year cycle. So the moon nutates, moon slowly moves up and down by 5 degrees in 18 years. So if we do survive for 18 years, we would get not just the thin strip plus minus 5 degrees around it. So there's more data to be collected if we survive long, but yeah, 1 year was just enough to get the science data.
Okay, we still have a couple of minutes. So a few questions on this side. I'll go here first because his hand was up first.
How do you plan to protect the telescope from an asteroid impact?
That's a great question. So a little bit primer to that is there are lots and lots of micrometeorites that are impacting Earth all the time, but the atmosphere is a great protection. Everything burns up in the atmosphere. On Moon, we don't have that. So we did the math on how many events are going to happen. Turns out for this telescope, we will see 1 wire cutting event per year. So a micrometeorite will hit the wire and the wire will get severed. There is a design that exists, which no one has actually built in lab, but there is a design that was created by Tethers Unlimited, where you intermesh 2 wires. And so even if 1 wire is cut, the structure doesn't fall because there's another wire right next to it and they're intermeshed. So we think that is a good enough design, and our design will be based on, I don't have a picture of it in this slideshow. So that's our first line of defense. But there's a second more fundamental problem is what happens if a large asteroid comes? we can't do anything. We just die. Yeah.
Who else had their hand up? You.
Yeah, hi. Thank you for the talk. So is there like no way to observe the same wavelength band from the Earth?
So some of these ideas that we talked of over here, some of these ideas are actually constellation missions around Earth Moon Lagrange point. In fact, DARE is a very strong candidate for that. ALPHA is another candidate. I was talking to someone today in the morning about ALPHA. So you could park a constellation of spacecrafts in Earth Moon Lagrange point and get this data. You could also do a sparse dipole array on a lunar surface. You don't have to go inside a crater, but these dipole arrays are like kilometer scales, like 20 kilometer cross 20 kilometer scale. So there's another. So there are other ways. That's a great thing about science. You're not supposed to have one approach to do the science. You're supposed to have multiple ideas, figure out which works, combine your resources and build something which is the best of everything. Yeah.
Okay, last question. I think one hand.
I have a couple of questions. So did you ever consider dual-use rovers which essentially anchor the mesh and then go away, do something else to save cost? And the second one, do we have a comparable, so what's the largest mesh structure that we deployed here on Earth? Like, do we have anything comparable to a kilometer square mesh structure?
So that picture I showed was 500 meters. So we don't have anything larger than 500 meters on Earth. Partially because this method of collecting signs on Earth is falling out of fashion. Because the sparse dipole array concept, there's actually a kilometer scale sparse dipole array owned by Caltech in Owens Valley, which is like, say, 2 hours away in the desert near Caltech. So this method of doing astronomy is falling out of fashion. Sparse dipole array are much better if you want to do it on Earth. No, but actually, like for example, I don't know about fast, but this Arecibo thing is actually a mesh. It's just the mesh is very much finer because again, I might be wrong, but Arecibo's smallest wavelength was I think in the centimeter scale. So your mesh was in the mesh size is in millimeter scale. You have to check it. So those are all mesh grids. They look, uniform because they're not resolvable at this distances. Yeah.
Okay, great. Let's thank our speaker again.
Thank you, everyone. Thank you all.